Okay, welcome back. 8.2 now, inconsistent and dependent of solutions. Okay. What is this? Well, it's just infinite and no solutions and infinite solutions. Okay, and this new context, and it works pretty much the same way. You'll end up with an equation or a statement rather that's false. In the other case, you'll sort of not have an additional variable solved for, so you won't have like z equals 3 or something. So anyways, but it's just the cases where you have like when we solve systems, infinite and zero solutions. So in case you didn't remember, when you have when you're solving a linear system and the lines are parallel, you have no solutions. When you're solving a system and the lines are the same, so they're right on top of each other, you have infinite solutions. Okay. So we talked about that back in the day, and that's what we're talking about again here. It's just we don't have the geometry to think about, and that will be hard. Secondly, we're now in terms of matrices, so you know it's not even sort of footed in something we're familiar with at all. It's a different sort of world. So the no solution case is going to be easy. The infinite solution case is going to be a little weird because there's different kinds of infinite solutions because of the geometry. Okay? So it's not just as simple as saying, oh, it's just this equation of a line. When you're thinking about three-dimensional space, for example, you could have a solution just being the equation of a plane, or if the planes are intersecting like this, the solution is the equation of a line. So there's weirdness there with regards to the solutions. Okay, so there'll be infinite solutions, and we want to describe the solution set, and it's not enough to just say infinite solutions all the time. You know, we want to know what kind of infinite solutions. So for example, here, when the infinite solutions all lie on this line, we're not saying that these other points are a part of that infinite set. You know, you have a point over here which is not included in the set. So we described our infinite solutions by just saying the equation of the line is the solution set. Any point that exists on that line. So we wrote it, the set of all x comma y such that y equals mx plus b. Okay, so in this two-dimensional case, that's very easy to accomplish, but when you get in higher dimensions, there's different kinds of infinite solutions based off of the geometry of the intersections. So that's going to be an annoyance. Let's just dive in here and take a look at it. Don't overthink it, just kind of act like a computer to a certain extent in the beginning. Get the handle of the calculations, and then start to iron out, you know, what is this thing that we're looking at. That's how I've always approached it. Okay, so let's look at number 2. This is the no solution case. You proceed just like you did, like we taught you before. Okay, so you're doing Gaussian elimination or Gauss-Jordan elimination, and you're trying to get ones on the diagonal and zeros in the lower triangular region. Okay, so 3, 5, 12. Okay, so my first step, my first objective is to get a 1 right there, and I can do that with very easily with a swap. Okay, so I swap row 1 and row 2, and I end up with 1, -3, 1, 5. And then I have 2, -4, 1, 3. And then I have 3, -7, 2, 12. Okay, then I want to get zeros below that position. So here and here. So I'll multiply the first row by -2. -2 row 1 plus row 2. And then -3 row 1 plus row 3. Okay, so let's do that. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Of course, the first row stays the same. Negative 2 times negative 3 is positive 6. 6 plus negative 4 is 2. Negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. Negative 2 times 5 is negative 10. Negative 10 plus 3 is negative 7. Negative 3 now. Negative 3 times 3, negative 3 times, we're going against the first row, 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times negative 9 is positive 9. 9 minus 7 is 2. Negative 3 times 1 is negative 3, plus 2 is negative 1. Negative 3 times 15, negative 3 times 5 is negative 15. Negative 15 plus 12 is negative 3. Okay, so now I go after pivot position. I go after this position here. I want a 1 there. So I'm going to multiply row 2 by 1/2. Okay, so I got 1, negative 3, 1, 5. 0, 2, negative 1, negative 3. And the more conscientious of you probably see, hey, there's a weird cancellation going on. If I just multiply this by negative 1 and add it to here, something odd would happen, right? So good, I'm glad you're thinking, but let's just go about it mechanically. So 0, 1/2, negative 1/2, and then negative 7/2. Okay. Oops, so 1/2 times 2 is 1. Sorry, this position is what we wanted, a 1 right there, right? Okay, so then I'm going to multiply this by negative 2 and add it to row 3. And something odd happens, right? So negative 2 times 1 is negative 2. Oh, oops, we've got to start with this guy. Negative 2 times 0 is 0. 0 plus 0 is 0. Then negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times negative 1/2 is positive 1. Positive 1 plus negative 1 is 0. Negative 2 times negative 7/2 is 7. 7 plus negative 3 is 4. Okay, so this row is weird, right? If you were to rewrite the system in our equation form, right? So x minus 3y plus z is 5, and then we have y minus 1/2 z is negative 7/2, and then 0x plus 0y plus 0z is 0 equals 4. There's our false statement that we would generally see when we're dealing with linear systems such that the equations were parallel to each other. Okay, whenever we tried to solve these systems, we'd end up with a false statement like this. Okay, so it's exactly the same in this context. This indicates that we have no solutions. Okay, so there's no place where, geometrically speaking, these planes will all three intersect. So there may be some intersection between two of them, but then there's an issue such that not all three are in the same place at the same time. So you really can't say there's points that are on all three planes in common. Okay? Right, so let's look at the infinite solution case, which I said was a little more complicated, right? And the only hard part is writing up your answer. But I think if you just take a leap of faith, it's not that big of an issue. It's just some reason it's hard to wrap your brain around at first. So let's dive in here. Let's look at number 4. And I have the matrix 5, negative 1, 3, negative 11, 3, negative 5, 6, negative 2, 2, and then 12, negative 4, 4. Okay. Right. So I need to get my, I need to get a 1 in that position. A quick thing you could do though is if you see a 1 here, rather than dividing all through by 5, do a swap. I'm going to have to multiply this row by -1 as well, so I'm going to try to embed all that in the notation. -1 times row 2, and I'm swapping that with row 1. Okay? So the result will be 1, -3, 2, 4, and then I'm putting row 1 in row 2's position, 5, -11, 6, 12, and then finally 3, -5, 2, 4. Okay. I need to go after zeros in those positions, so kill 2 birds with 1 stone. -5 times row 1 plus row 2, and then -3 times row 1 plus row 3. Okay. So row 1 is unchanged. Row 2, so -5 times 1 is -5, plus 5 is 0. -5 times -3 is +15, plus -11 is 4. -5 times 2 is -10, plus 6 is -4. -5 times 4 is -20, plus 12 is -8. Keep going. -3 times 1 is -3, plus 3 is 0. -3 times -3 is 9, plus -5 is 4. -3 times 2 is -6, plus 2 is -4. -3 times 4 is -12, plus 4 is -8. And you see something odd. The more conscientious of you probably see that. We have the same row here and here. Okay. For the moment, let's pretend we did not see that and keep on going as a computer would. Okay, so we want to obtain a 0 in this position, or sorry, a 1 in that position. So I'll divide row 2 by 1/2, or multiply by 1/2, excuse me. Sort of getting in a hurry now because I know I have to be somewhere. Okay, and then I need to get a 0 in this position. Okay, so I'll multiply row 2 by -4 and add it to row 3. Okay, so row 1 stays the same. Row 2 stays the same. And then row 3, I'm going -4 times 0 is 0. 0 plus 0 is 0. -4 times 1 is -4. -4 plus 4 is 0. -4 times -1 is +4. 4 plus -4 is 0. -4 times -2 is +8. 8 plus -8 is also 0. Okay. So this is a big red flag here. So just like before, this says kind of that we have infinite solutions. Okay, so this is telling us infinite solutions. We can transfer it back into equation form. X minus 3 y plus 2z is 4, and then y minus z is -2, and then 0 equals 0. Okay, so this is kind of like the true statement that would result when we looked at infinite solution cases and systems of linear equations in 2 variables, right? So in these cases, we would always end up with a true statement when we try to do the substitution or the addition method. So this indicates infinite solutions, okay? So it's true infinite solutions. The only problem now is trying to figure out what exactly are those solutions, because it's not everything in the universe. It's just a certain subset of, in this case, 3-dimensional space we could think of. Okay, so what we're going to do is sort of let z be an imaginary variable something, and the book usually calls it t. Okay, so we're going to say let this one variable z, this bottom variable that kind of went away, equal anything you wish. And then we're going to solve for the other equations in terms of t. All right, so I have y minus z is negative 2. In other words, y minus t is negative 2. Okay. So we'll have y equals t minus 2. And then we substitute this expression and this expression into the first equation. So it's kind of like we don't know what z is, so let's just call it anything we want, and then do the normal back substitution. Okay, so over here then we have x minus 3 times y, which is now t minus 2, and then plus z 2 times z, which is t, equals 4. Okay. So we'll have x minus 3t plus 6 plus 2t equals 4. And then we have x minus t plus 6 equals 4. And so x equals t minus 2. Right? So our solution set is the set of ordered pairs such that they have the form t minus 2 comma t minus 2 comma t. So anything of that form is a solution. So in retrospect, now that I look at it, it is very similar to what we were doing with our previous work in Gaussian elimination. It's just once we get to this step here, this final step in Gaussian elimination where we back substitute everything into a system of equations, we won't have z equaling something. So what we've done here is say, hey, I don't know what z is. Let's just call it something. Let's call it t. And then we do our back substitutions based off of this. So instead of having y minus 3 times 1, we'd have y minus 3 times t, and then solve for y, so you'd have 3t minus 4, and then back substitute these two into this, and you get it in terms of, okay, so hopefully you can somewhat stomach that idea. Okay. The last section in here are non-square systems, and it's kind of just similar to this, except we've thrown away this one row. Okay, so you're working with a matrix that looks like that. Basically just 2 rows and nothing else. Okay? And it's very similar to these infinite solution cases. Okay, so let's take a look at that very quickly. Section 3 in my notes, non-square systems. Problem 20, we have the system negative 2x minus 5y plus 10z is 9. And then x plus 2y minus 4z is 12. Okay, so first thing we want to do is transfer it into a matrix. So I have negative 2 minus 5, 10, 9. And then 1, 2, negative 4, and 12. We're going to work this matrix the way we have been doing the Gaussian sort of elimination to get it into this form where we have 1s on a diagonal, if possible. Okay? So the first thing I can do is get a 1 in this position here. So I'll swap row 1 and row 2. So I have 1, 2, negative 4, 12. And then negative 2, negative 5, 10, 9. Okay, next I'm going to try to get a 0 here. Right. So I'm going to multiply the first row by 2 and add it to row 2. So I have 1, 2, negative 4, 12. And then 2 times 1 is 2. 2 plus negative 2 is 0. 2 times 2 is 4. 4 plus negative 5 is negative 1. 2 times negative 4 is negative 8. Negative 8 plus 10 is 2. 2 times 12 is 24. 24 plus 9 is 33, which seems a bit off. Let me look again. 2 times 12 is 24. Plus 9 is 33. What did I do wrong? Maybe there's a mistake in my notes. I copied it wrong. Sorry, there should be a 1 here. Sorry. Okay, so it's not 33, it's 43. Sorry about that. Okay, now you want to get a 1 in this position. So you try your best to reproduce this nice 1 on the diagonal form. Sometimes you have to have 0 here, and a 1 here. And in those cases, you just kind of revert back to our equation system and see if you could solve it from there. Okay, so anyways, I'm going to have to multiply by positive 1 or negative 1 here. So negative 1 times row 2. I'm just making sure I'm on track with my notes here. Yeah. Okay, and so we get 1, 2, negative 4, 12, and then here 0, 1, negative 2, negative 43, and then we can convert back into our equations. So x plus 2y minus 4z is 12, and then y minus 2z is negative 43. And then it's very similar to what we had with the infinite solution case. So, I mean, we could try to solve for y, but let's just say z is anything we want. Again, let's call z t. Okay? And then back substitute. So y minus 2 times t is negative 43. So y is equal to 2t minus 43. And then back substitute all of this into the original first equation, sorry. So x plus 2 times y, which is now 2t minus 43, minus 4 times z, which is t. Okay. So I get x plus 4t minus 86 minus 4t equals 12. The 4t's cancel. I have x minus 86 equals 12. So we'll get a nice solution for x. X equals 86 and 12, 6, 7, 8, 9, 98. Right, so our solution is a set of all ordered triplets such that the first coordinate is 98, the second coordinate is 2t minus 43, and the third coordinate is just plain old t. Okay, okay, so that's the idea. Hopefully that'll get you through the homework. Okay, I'll see you.